Hello. Can you hear me? See me? Yeah, perfect. Beautiful. So, yes, apologies for the late publication of the work. We're still polishing it up, polishing it out. The topic is LCR circuits. So you know R and C. So it's a resistor and a capacitor. And L is an inductor, something that you don't need in school, but nevertheless it's super important in circuit theory. Okay. Right. So I'm going to share my screen and let's get started. And first, let me tell you, well, the RC circuit. The circuit you're already familiar with. Please tell me who's familiar with the RC circuit. Yes or no? I'll go check chat. Yes, yes. So what about Noah? What about you know? Familiar, not familiar. Yes, okay, familiar. So you already know how it works. So we take a battery and we take a capacitor. I should have used like this. Yeah, that makes more sense. Battery, a switch, and we can charge the capacitor like this. So we charge the capacitor. Now the capacitor is charged. So obviously positive charge flows onto the right plate, and the negative charge flows on the left plate. It's not really, because the negative charge from the right plate flows into the battery, but it's not. What about such little things? So sorry. In circuit theory, it doesn't really matter how you look at it. Okay. Right, so electrons move. And now let's look at the current. So the current is 0 because the switch is open. And now the current will change in a familiar way, which you already know. This is the discharging a capacitor. Discharging a capacitor. Discharging curve. And the charging curve is very similar. So you just take a resistor and you put the current here. Current needs to be open. Okay, so discharge the capacitor and going like this. Same curve. So open it up, discharge, close it. And this is charging. Okay, so you understand how a capacitor works. It stores some charge. So let's have a look. So let's remove this resistor. So you can charge the capacitor, open the circuit. So it has stored some charge, and now it can discharge through a resistor. Okay, so fairly straightforward. Now, this is how the RC circuit works. I will do the differential equations, but I want to go through all types of circuitry first, just to make sure that we have enough time to do the differential equations. The LR circuit. So the LR circuit has an inductor. This is an inductor, and it has inductance. The inductor works by producing a magnetic field inside. So it's a coil with a magnetic field. And now, because it has a magnetic field, Lenz's law applies. If you start increasing the current through the coil, so when the switch is closed, when switch is closed, the current starts to increase. The coil, the induction coil produces a magnetic field. This magnetic field increases. Yeah, because a coil produces magnetic field, and this magnetic field increases. Does that make sense? Coils do not like change. So Noah, Judith, does it make sense to you that the coil produces a magnetic field, this magnetic field increases? All right, and I think Jasmine has joined. Jasmine, are you on board with everything so far? What did you miss? We were talking about the charging and discharging of a capacitor through a resistor. So this is the discharging of a capacitor. This is the current time graph. And this is the charging, which is the same graph, just charging a capacitor. So far, we've discussed charging and discharging capacitors. And now we're talking about the LR circuit, something you're unfamiliar with. So when switch is closed, the current starts to increase. Yes, because that's what current does. The induction coil produces magnetic field. This magnetic field increases. Coils do not like change. The coil will induce a current in the opposite direction. This will reduce the overall current. So the current changes gradually. Does that make sense? So let's have a look. Let's have a look what it does. So we have a battery, a current, a resistor, and a switch. Okay. what do you think will happen when I close the switch? What happens to the current? There's no inductor yet. So just tell me. Yeah, jumps to a maximum. So let's have a look. Bam. Okay, let's increase the voltage a little bit just to be a bit more dramatic. Okay. Let's make it 15. Right. So open, 0, closed, jumps up. This is the typical behavior of a switch. I mean, like in reality, it does not, you cannot have this. It will still be a smooth-ish curve, but it's very difficult to detect. Okay, so now let's introduce an inductor and see what it does. Introduce an inductor in the circuit. An inductor is simply a coil of wire. Now, inductors don't like change. So let's have a look. So the current is 0, and now we close the switch. What happened? Now, before this webinar, did you know about inductors and how they work? Well, we did mention them in the previous assignment. So did you know that this would happen if you introduce a coil into the circuit? Yes or no, please? So yes from Adam. Not exactly. So this is a simple effect. So coil just generally likes to keep the things the way they are. So it will try to keep the current at 0, which is impossible, of course, but it will try to hold the barrier for as long as possible. And when we open the switch, well, here when we open the switch, it just drops to 0. Because the circuit is incomplete and no current can flow. So actually, it's a very interesting thing. What actually happens, because the inductor stores energy. The inductor stores energy, and the energy stored in an inductor. Energy of an inductor is 1/2 Li squared, where L is the inductance. It's the energy stored in an inductor. So if there's a current flowing in an inductor, there's energy. So what actually happens when you open the switch? It seems weird, right? Because it had energy and now suddenly this energy disappears. That's not possible. Does anyone know what happens to the energy? There's actually a question in the assignment about this. Well, not exactly this one, but a similar one. The inductor stores energy. Okay, if I forget to tell you what happens to the energy, I will. What happens? happens to energy once we open the switch. This is actually a really good question. Okay. Now, let's make a parallel circuit with another resistor. And we will be measuring the current here in the inductor. Oh, so this time. Okay, so the current is 0. When we close the switch, the current starts to build up just as it does in the previous one. So the current builds up slowly, because if you look at this current, it's not slow, it's just instant. Okay, so the current here is established. So we have just a normal circuit. There's nothing extraordinary happening here. So the current flows through the resistor. Now the current is not changing, therefore the inductor doesn't do anything. Okay. The voltage on the inductor is actually 0. Voltage on the inductor is 0. The voltage of the resistor is 15. Okay. So the voltage on the inductor is 0. So the inductor doesn't do anything because there's no change in current. Now look what happens when I open the switch. When I open the switch, the inductor starts to work. Okay. So look once again. So let's increase the inductance and reduce the resistance, I guess. Actually, no, this one. Let's make it 10 ohms. Oh, actually, we need to increase the resistance. Yeah, let's increase the resistance. Okay. So close the switch. And you see that the current grows slower because the inductance is bigger and the resistance is bigger. And now it starts dropping. Once again, closing it, gradual increase in current, and then constant current. And it drops. So what have we learned? What have we learned about inductors? Inductors. Somebody help me?
They can be temporary stores of energy.
Very good. Yes, they can store energy. They oppose the flow of a changing current. No, they oppose the change. They don't oppose the flow, they oppose the change. So if the current is increasing, it will try to decrease it. And if the current is decreasing, it will try to increase it. Okay. So it will, if a current is decreasing, is increasing, it will increase it. Increasing it will decrease it. If a current is decreasing, will increase it. In other words, will when you switch on the power supply, look, when you switch on the power supply, the current starts to increase, and then you switch off the power supply and the current starts to decrease, but you can see that it's still flowing. So it can keep current flowing just like a capacitor does, it just in a slightly different way. So it does a job very similar to a capacitor. Can keep current flowing when the supply is cut off. Okay, that's interesting. All right, does everything make sense so far? Yes or no? Oh. Unfortunately, some people have disappeared. That's yeah, it's a pity. Anyways. Right. Now we look at the next type of circuit, which is probably my very favorite circuit, the LC circuit. Now, this circuit does not contain a battery. Well, how can a current flow in that circuit, you would ask me? How can you start a current? Well, you need to charge the capacitor. When you charge the capacitor starts to discharge through the inductor. But the inductor does not like change, and once the current is decreasing, because as the capacitor discharges, it will try to increase the current. So it will keep current flowing even when the capacitor is discharged. It will keep current flowing, charging the capacitor. So the inductor will charge the capacitor, and then the capacitor will discharge in the opposite direction. So first the capacitor discharges this way, and then it charges, and then it discharges the other way. Let's have a look. This is the absolutely beautiful circuit. I just love it. So inductor and a capacitor. So we need to charge the capacitor, of course. And for this, we use a battery. And okay, we'll use a switch. We'll use a switch to charge the capacitor. Sorry. That's awkward. The switch must go here. So now, so the capacitor is not charged. So now I put a voltmeter across the capacitor. So the capacitor is not charged. And now I charge the capacitor and it almost instantly goes to full charge. So 9 volts in this particular case. And now when I close the switch, the capacitor will start to discharge through the inductor. But then, because the inductor will keep the current flowing, so I'm just increasing the inductance. The inductor will keep the current flowing and it will charge the capacitor in the opposite direction. So let's have a look. So closing the switch. So the inductor goes back. Now the capacitor is charged the opposite direction. I changed the inductance just to get a better sine curve. So you can see the capacitor charges and discharges, charges opposite way. So now it's plus minus, and now it's minus plus. Okay. Have you seen this circuit before? Has anyone seen this circuit before? Please let me know. Yes or no? All right. In a tutorial. Okay. In a tutorial like electricity tutorial. Or electronics. Rather electronics. All right. RLC Circuits. RLC Circuits last week. Oh, okay. In the tutorial, I see. Yeah, that makes sense. In your the COMPOS tutorial. Yeah. So this is a circuit. So it's in very interesting one, and it obeys the same laws. It's the same law as simple harmonic motion, and I will show this to you. So let me take a snapshot. And once the capacitor is discharged, the inductor keeps the current flowing, charging the capacitor in the opposite direction. Let's make a note of this. Once the capacitor is discharged, the inductor will continue the current charging the capacitor, which will be opposite direction. Not really an AC generator because it will die out. The oscillations will die out because here you have an exchange of energy without losing anything. So it's like a pendulum. Yeah. So can you use a pendulum to generate AC? Well, not really. But if you keep charging the capacitor, yeah. I'll show you I'll show you how an AC behaves in such a circuit, which is quite interesting. And let's check something out. The time period for such an oscillation is 2 pi square root of LC. So if L increases or C increases, the time period increase, right? If to increase T, increase L or C. To increase L, you simply increase the number of turns, or to increase C, you bring the plates closer together, or you make the plates bigger. Okay, so both these, so you can bring the plates closer together, or you can make the plates bigger. This will increase T. Frequency is, of course, the 1 over T, so it's 1 over 2 pi square root LC. And omega is 1 over square root LC. Those things you are familiar with. You know that omega is 2 pi f, which is, so it's 1 over LC. Let's check that it actually works. So we have okay, this is a good point. So we have, what do we have? We have the capacitance is 0.1. Capacitance is 0.1 farads. That's a huge capacitance. The inductance is 5 Henry. The inductance is 5 Henry. And the time period must be 2 pi square root LC. Yes, the recording will be available. 2 pi is LC, so that is 2 pi square root of 0.1 times 5. So 4.44 seconds. And as we can see from here, half period from here to here, that's half a period, and that's about 2.2 seconds. 2.2 seconds. So the time period is 4.4 indeed. So it does work. Now, the next type of circuit, so I'll just delete that. The next type of circuit is the LCR circuit. Here you have a capacitor, you have an inductor, and you have a resistor now. So what do you think the resistor does? What do you think the resistor does in the circuit? So what increases? Good point. Well, it does have a slight effect on T, but that's not the most dramatic effect. Look at the oscillations. What can you tell me about them? there's no energy dissipation. Yeah, it could produce a damping effect, of course. The amplitude would decrease over time. Let's have a look. So I wonder if I can. Okay, this is a good point to start. So we cut this and we introduce a resistor. Now, watch carefully what happens to the graph, the resistance. Let's make it 0.1 ohms. Look at that. Damped oscillations. It's the same as a damped oscillator, like a swing. Right. And if you have a very small, inductance and very large capacitor, and you have a lot of damping, so let's say 20. Let's charge this. Okay. Open this. Oh, sorry. Well, what I wanted to show is overdamped. So this is underdamped oscillations. Underdamped oscillations. Underdamped. Underdamped. And this is like if you have underdamped, just like underdamped. Then you have critical damping. Critical damping. And you have overdamped. Overdamped is like this. Overdamped. The red is critical damping. Critical damping. And the black one is underdamped. Okay. Now forced oscillations. Forced oscillations and resonance. Oscillations and resonance. When do we have resonance? Can somebody remind me? Yes. Resonance occurs if the frequency of the forced oscillations, of the frequency of the driver is equal to the frequency of the natural frequency. Well, we know the natural frequency is 1/2 pi LC. That's the natural frequency. So the frequency of the driver matches this. Then we have resonance. So let's have a look. We'll have a resistor. We have a capacitor. We have an inductor. Let's make the capacitance 0.05. The inductance, let's make it 1. The resistance, let's make it 2 ohms. 2 ohms. And this is the AC voltage. So this is an AC power supply. And we have the current chart. Okay. So we have forced oscillations. So this is an alternating power supply, and it's forcing oscillations in this circuit. Okay, so the capacitance is 0.05. The capacitance is 0.05 farads. The inductance is 0.1 Henry. 0.1 Henry. So the frequency, the natural frequency is 1/2 pi square root 0.05 multiplied by C by 0.1. So the frequency is 1/2 pi square root 0.05 times 0.1. 2.25 hertz is the natural frequency. So if I make my frequency 2.25, I should have resonance. So the current should increase dramatically. So the amplitude of the current should increase very much so. So let's have a look. 2.25. We won't allow. It only goes up to 2. Okay. So what can I do? I can reduce the 0.2. Zero point 0.228, this is going to 0.228 Henry, and then the frequency will be 1.49 hertz. 1.49. So let's have a look. 0.228. So we need to change the induction 0.228. 0.228. And now we need to change the frequency to 1.49. So 135, let's have a look. The amplitude is about 5 amps. So the maximum current is about 5 amps. And let's start increasing it, getting closer to 1.49. Something. Well, yes, you can definitely see something's happening. So the amplitude is increasing, not as dramatic as we want it to, but it does take some time. And you can see fire coming out of the resistor and the power supply because they're not coping. You can definitely see that the maximum current increased to well, there's quite a dramatic increase. So let's pause it. So reduce the capacitor. Let's start again. So 25. So it goes from 25 to 50. So it keeps increasing. So this is resonance, or at least very close to resonance, because because it's not exactly that number. So let's see if we can change the inductance. 2.29. No effect. 2.7. 6. 2.25. It's actually decreasing a little bit. 2.28. So the closest one. So yes, you can have a resonance. So this is an alternating current power supply. And if the frequency of the supply matches the natural frequency of the circuit, you will have resonance. Now let's just change the frequency to a different value so you can see that actually it is resonance. So you can see that. You can see that definitely a massive decrease in the current. Let's see if it stabilizes at a different value. Okay, so it's oscillating, but nowhere near to the 50 amps of current that we had at resonance. Let's try higher frequency. Let's try 2 hertz. So a larger amplitude, but still nowhere near the 50 hertz. And at 1.49 hertz. So the voltage is the same at 1.49 hertz. It starts resonating. Okay. And of course, you should be familiar with the resonance curve. That when you have the frequency with the forced oscillations and the frequency of the first forced oscillations and the amplitude. The amplitude in this case is the current, and here is the frequency. This is the natural frequency, which is square root of LC. So 1 over square root of LC, sorry. And the resonance curve looks like this. So you have a maximum of current at resonance, and then it decreases. Okay. So where do we use that? Well, we use that for radio. Your radio receiver, the antenna, for example, the antenna receives a wave coming in. So you have an antenna, and an electromagnetic wave comes in. It comes in and it starts to oscillate. The electrons inside the antenna, a wave and an electromagnetic waves comes in. It produces tiny oscillations in the antenna. The antenna is part of the RLC circuit. Part of the RLC circuit. Good. Right. And if the natural frequency is equal to the frequency of the wave, you have resonance. You can listen to BBC Radio 2. Okay. What's the frequency for BBC Radio 2? Does anyone remember? I'm not sure, but Radio 2, my favorite radio. It's 88 to 91 FM, so the smallest frequency, so it's 88 to 91 megahertz. It doesn't mean that every single frequency in that range is BBC Radio 2. It just in different regions, different parts of the UK, you have different frequency. At least that's how I understand it, because I don't know, in other countries, they tell you exactly. For example, Radio 1 is 88.7. Radio 2 is 89.3. They tell you exactly. So I'm not sure why they give this range for Radio 2. I would be interesting to find out. Anyways, so let's say BBC Radio 2 is 88 megahertz. So for example, where you live, the frequency is 88 megahertz. That means if your radio receiver, the capacitor and the capacitor and the inductor have exactly matching this, so 2 pi 1 over 2 pi square root LC, if the frequency is that, then you would be able, the tiny oscillations produced by the radio wave will cause a big current in the circuitry. Does that make sense? Okay. And let's look at this. So go back to this. Let's measure the voltage. Let's measure the voltage on the supply. It's 9 volts. The voltage on the power supply is 9 volts. And let's measure the voltage on the capacitor, for example. It's 100 volts. So you can see how tiny voltage on the oscillator can produce a huge voltage on the capacitor. So in this case, the radio wave coming in produces oscillations in the circuit, but they are tiny, they're less than tiny, they are microvolts. But in order to listen to the radio, you need it to be something significant. So if your circuit is tuned to that particular radio station, then you will hear a signal. You would see resonance, and that resonance means that there is sufficient current to produce a sound. At resonance, the current is sufficient to produce a sound. Now, there's a value called the root mean squared value. So the current root mean square current, that's the average current in the circuit. And the range of frequencies by which the current remains significant is called delta omega. And delta omega is called the bandwidth. So, for example, if you have radio stations like 88.7 megahertz, then the next radio station can only be at least one bandwidth away. Okay, so let's say the next radio station is 89.2. That means the bandwidth must be 0.5 megahertz. So delta F, well, it's delta omega and delta F, the same thing. I hope you understand that. Delta F is 0.5 megahertz. It's the shortest distance between two radio stations. Okay, because you can have resonance. I mean, if you deviate from the frequency, you still hear a signal, not as big. So the resonance is not as great, but it's good enough. So how did old radios work? So radio receiver circuitry. Vintage. So you've probably seen these things. Copy image. Oh. It's the wrong image. So the most important one was this knob. Well, volume is easy. It's just a resistor, right? Not the main resistor, but just a resistor that is connected to the supply. So the volume is a variable resistor. That's a variable resistor. And the tuning knob, so variable capacity. variable capacitor, variable inductor. Well, this is not as easy to understand, the variable inductor. Oh, I think this one. Yeah, something like this. Variable capacitor and variable inductor. So the variable capacitor works quite interestingly. So you have these moving plates. So these plates are stationary. So these are fixed. And these plates can move. These are movable. When you turn this knob, these movable plates go in between the fixed plates. And that increases the area of the plates, of the capacitor plates, and it brings them closer together. So you're increasing the effective area, and you're bringing the plates closer together because they go in between, so the gaps between the plates decrease. So twisting the knob clockwise increases the capacitance. And this knob is the tuning knob. Here it is. It's connected to a variable capacitor. So you have a variable capacitor, as I said. It's a variable capacitor. There's an inductor. And there is the power supply. Well, there is a resistor, of course, which is just the resistance of the circuit. And of course, there's the power supply, which is the antenna. The antenna is the power supply. And you tune this a variable capacitor. And the frequency is 1/2 pi square root LC. So if you vary the capacitance, you can change the frequency. Or you can use a variable inductor. It's the same knob. It's the same knob, but different device. It's a variable inductor. In this case, it's a fixed capacitor and a variable inductor. In resistor and the antenna. It's a power supply. So you twist the knob, and this connection moves left and right, effectively increasing the number of loops. So it changes the number of loops, which increases the inductance, or decreases the number of loops to reduce the inductance. So this is a variable inductor, or a variable capacitor. In both cases, it's the same knob, but depending on what you like more, what's more available, what's cheaper, a variable capacitor or variable inductor, you would design your radio. So now you can actually build a radio, and it's not that difficult. And now I'll show you something that actually blew my mind when I was in school. Now, imagine you have a circuit. Imagine you have an LC circuit. Consider an LC circuit. this is the capacitor, and this is the inductor. In order to increase the frequency, so radio signals are high frequency. Radio is high frequency. So shortwave radio is high frequency. So you want to increase the frequency of the circuit. We want to increase the we want to increase the frequency. And we know that the time period is 2 pi square root of LC. So what are the two ways to reduce the time period? So to increase frequency, the capacitance has to go up or down. Capacitance must go down, and inductance must go
Down too.
down. Very good. So the capacitance must go down, inductance must go down. So how do we increase the capacitance of a capacitor? How do we decrease? Sorry. Physically, we move them further apart. Yes? Move plates further. What else can you do to decrease the capacitance? You can either move the plates further, or you can
Reduce the area.
So we increase the distance between the plates and we make the plates smaller. How do we reduce the inductance? Less coils. So carry on. Increase the distance even further. And then reduce them even further. What do you get? So they reduce the coils to 0. That minimizes 0 coils. That means minimum inductance. And straight wire. So the plates are as small as they can get. Small. Max distance apart. That is minimum C. What does this look like? Have you seen this before? A bit more specific.
A charger.
What? No, not a charger. On a car, this is an automobile. It's an antenna. It's an antenna. So this, I don't know if this blows your mind, but it blew my mind completely. So an antenna is an LCR circuit in itself. It's a circuit, it's a straight wire, has very, very low capacitance. It has a very, very low induction. And so to increase the frequency, you basically unwrap your LC circuit into a straight wire, which is also known as an antenna. Okay, whose mind is blown? Yes or no? Right, does everyone understand what just happened? So we just took the LC circuit, and an antenna is an LC circuit where you're striving to reduce the frequency by reducing the capacitance and reducing the L. Okay, and now as promised, I want to go through some of the differential equations responsible to each of the circuits. So the first one is the easiest one. You've met it already. So you know that zero coils does not mean zero inductance. Zero coils means the minimum possible inductance. A straight wire has inductance. That's why if you have a straight wire, current cannot grow instantly. Like in this, even if you have a short circuit, and a switch, a switch and a short circuit. When you close the switch, current will not grow instantly. It will take some time to increase because even straight wires have inductance. And oh yes, and I promised to tell you about this question. What happens to energy once the switch is open? Remember, we had a current established in a circuit. And the current, we just open the switch. So you have a battery, you have a switch that is open suddenly, and here you have a resistor and a coil. Well, look at this. Look at this switch. Bam, bam. Does it remind you of anything? Does this open switch remind you of anything? Yes. So when you open the switch, what happens is you have an oscillating circuit. And it will oscillate and dissipate the energy through the resistor. It's just very low capacitance, therefore it will be very high frequency and very high energy dissipation. So energy stored in the inductor will be dissipated as heat. Now, what if there's no resistance? Let's suppose it is made of a superconducting metal, and there's no resistance whatsoever. What would happen then? If resistance is 0. what would happen? It's just a normal LC circuit. Well, okay, I have to mention that LC circuits will not go on forever. Unlike a perfect swing, right? Like a perfect swing in with no friction, which will keep going on forever. An LC circuit will not go on forever because it will produce electromagnetic waves. So the energy will be dissipated as electromagnetic waves. The energy will be dissipated as electromagnetic waves. Right, so we are oscillating a circuit, and every oscillating circuit will also produce electromagnetic waves. It's just usually the amount of electromagnetic waves produced is very small compared to the heat produced. Therefore, we can ignore the electromagnetic waves energy. But here, there's no energy lost as heat. Therefore, all the energy will eventually be dissipated as electromagnetic waves. Okay, so that's quite cool. Right. Okay, and some differential equations. Well, the first one is the RC circuit. I'll go through them quickly. Do go back through the recording if you are confused. So the RC circuit, so we have, so this one should be familiar to you. We have a charged capacitor and a resistor. Charged capacitor, so let's say this is plus, this is minus. Current will flow anticlockwise, minus plus. So voltage on the capacitor must equal to the voltage on the resistor. The voltage on the capacitor is Q divided by C, is the charge divided by the capacitance. And the voltage on the resistor is equal to IR. Now, current is also known as the rate of discharge. Current is the rate of discharge of the capacitor. So it's minus dq over dt. So this must equal to, let's put it this way, Q charge on the capacitor divided by capacitor is equal to minus dq dt R. Okay, separate the variables. So we have dq over q is equal to 1 over RC times t and minus. So I just rearranged that. Oh, sorry, dt. So I multiply by dt. I just wiggled things around until I got this. Now, it's a differential equation, and I can integrate that. Now, RC are constants, so we can do this. So Q changes from Q0 to Q final. So this is Q0. Well, let's not do Q final. Q final is just Q. And time changes from 0 to t. The integral of dq over q is logarithm q. So it's logarithm q minus logarithm q0 equals minus 1 over rc. And the integral of dt is t. So it's t minus t0. T minus 0. And here we get logarithm q over q0. is equal to minus T over RC. Q is equal to Q0 e to the power minus T over RC. This is a formula which is familiar to you. Okay, you can find the voltage now. The voltage is Q over C. So voltage is Q over C. So you have voltage is equal to V0 E minus T over RC. And in a similar way, you can find that the current is equal to I0 E minus T over RC. Okay. Did you know how to derive these formulas before? Have you ever derived them before? Yes or no? Okay, and Judah, have you derived this before? Because they are in parallel. Okay. So the next question, do you think you can derive these formulas now? Okay. In the last one, you use the Ohm's law. So here you use the Ohm's law to find the current. So I is, what did I say? Voltage is IR. So current is voltage divided by R. Sorry, yes. Now the next circuit is the LR circuit, and we'll consider the differential equation for the LR circuit. LR circuit. So you have an inductor and a resistor and a switch. The switch is kind of a big deal here because without the switch, it won't really work. And so this is the resistor, this is the inductor. So the voltage on the inductor is equal to the voltage on the resistor. Oh, sorry, and no. What am I doing? Apologies. There's a battery here. There's the EMF. So this is plus minus. This is plus minus. So there's you label with plus, high potential with plus and low potential with minus. Now the current will be pushed clockwise. So the inductor will be pushing anti-clockwise, plus minus. So the battery will be pushing clockwise. That means the inductor will be pushing anti-clockwise. I hope that makes sense. So the EMF is equal to the voltage on the resistor plus the voltage on the inductor. EMF is equal to IR plus L di dt. This is something you just need to know about inductors. So the voltage on the inductor is L di dt. Now we double check for signs. So the current is increasing, so di dt is positive. L is positive, so therefore this is positive. So the sign is correct. So you can double check yourself, like, does it make sense? Now, this is from the moment we flip the switch. So we rearrange this we get minus L di dt is equal to IR minus EMF. We separate the variable, so multiply by dt, so it's minus di divided by IR minus EMF is equal to 1 over L dt. Now, this integral is much harder than this one. I'm going to put the minus here and make this plus. Just multiply by -1. I'm allowed to do that, obviously. So this is an easier integral, so I won't get confused with the minus. So now I integrate it. So I integrate current. Current changes from 0 to I. I is the final current. And time changes from 0 to t. Good. And I integrate. This integral is dx over ax plus b. It's logarithm ax plus b 1 over a plus c. So I hope you see that this integral is this integral. And here I can do 1 over r logarithm IR minus EMF minus 1 over r logarithm EMF, because 0, logarithm minus EMF 1 over L times t. Now IR is less than EMF, because IR is the voltage on the resistor and it cannot be bigger than EMF. So we have to flip this because it's a modulus. IR is less than EMF, therefore we have 1 over R logarithm EMF minus IR minus 1 over R logarithm EMF equals minus 1 over LT. So logarithm, apologies that I'm rushing. I do want to do another equation. EMF equals minus 1 over RL. Oh no. R over L T. And we rearrange this. We rearrange this to get EMF minus IR equals EMF E minus R over LT. So the current is EMF open bracket 1 minus E minus R over LT over R. Or it could be written as I final multiplied by 1 minus E minus R over LT. Right. Well, I not final, I stable, I0. And we did see this picture because the graph looked like this. The graph looked like this. Something very similar to a skydiver. So this is I0. This is the maximum. Well, Imax. Let's call it Imax. Sorry. Max, the maximum current, and this, so time. And it does look like this. And remember, if you draw this graph, it looks like this. And here it was. Here it is. Here's the graph. Finally, I'll do one more. I won't do the LCR, but I will do the LR circuit, LC circuit. LC circuit. So what we have is we have a charged capacitor. A switch, an inductor, capacitor C, inductance L. So we start with the Kirchhoff's law. So once we close the switch, when the switch is closed, we have the voltage on the capacitor is equal to the voltage on the inductor. It has to be like that. The voltage on the capacitor is Q over C. Yes, Q over C. And the voltage on the inductor, as we already know, is, so this is positive, negative, so it's L multiplied by di dt. Di dt. Now, we know that the current is the rate of discharge of the capacitor. So current is minus dq over dt. That means di dt is the second derivative of the charge. So it's minus d squared q over dt squared. It's the second derivative. So we can write this as q over, we can drop this LC down, q over LC is equal to minus d squared q over dt squared, which is also known as minus q double dot. So q double dot is equal to minus 1 over LC q. Does this equation look familiar to you? Yes, acceleration is minus omega squared x, or x double dot is equal to minus omega squared x. And if you remember, the solution to this equation was x is equal to a multiplied by cos omega t plus phi, where phi is the starting phase. That's the solution. So in a similar way, the solution here, well, I mean, we could go through the whole process of second order differential equations, but if you know the solution, you don't need to solve the equation, right? If you already know the solution. And the solution to this equation is q is equal to q naught multiplied by cos omega t plus phi. You also can see that omega squared is 1 over LC. So omega is 1 over square root of LC. Frequency is omega divided by 2 pi, which is 1 over 2 pi LC. And the time period is 1 over frequency, which is 2 pi square root LC. So all formulas which you are already familiar with from earlier today. So you got the time period, the frequency, the angular frequency, and you got the equation. And now if you go for the current is equal to the derivative dq dt, or minus. So it's going to be minus q0 omega sine, well, this is a minus sign, so it's plus sine omega t plus phi. And you can already see that this is the amplitude of the current. The maximum current is q0 omega. It's interesting to know. So current is I0 sine omega t plus phi. So the current is cosine, sine. So it's a phase of, it's a pi over 2. It's not in phase with the charge, which makes sense. Current, because when the charge on the capacitor is maximum, the current is 0. And when the charge on the capacitor is 0, the current is maximum. So they are not in anti-phase, but they are pi over 2 out of phase. They are out of phase. That's the word there. Current and charge, Q and I, are out of phase. Out of phase. And finally, voltage, but voltage is simple. Voltage is voltage on the capacitor and voltage on the resistor. They will behave differently. Of course, we're interested in the voltage on the capacitor in this particular case. So it's Q over C. So it's V0 cos omega t plus phi. Phi is the initial phase. Phi is the initial phase. Or phase. It depends on where you start. Do you start with the capacitor charged, or do you start with the inductor carrying current? Right. Just like a swing. Do you push the swing, or do you pull it and let it go? This is why. So in one case phi is 0, in the other cases phi is pi over 2. Yes. I'll stop here because I can go on. This is one of my favorite topics in physics. I can go on forever, but I do need to have dinner. So I hope you enjoyed today. Hope you learned new stuff. And yeah, I'll see you. Good. I'm very glad that you did understand everything. That's really good. Okay, see you next week. Oh, it might be that David Vaccaro is going to lead the next week's session. We haven't had a discussion on this yet, but we'll see. All right, see you.